Hello, MS6000 students. This lecture will cover Chapter 5, Hypothesis Testing and Statistical Inference. So we are going to go ahead and breeze through Chapters 3 and 4 because this should be a review for most students. And if it is not a review, I highly suggest going through, looking at both Chapters 3 and 4, kind of skimming through, making sure that you have a good understanding of all the concepts, because you'll find that statistics builds on itself, so you should be familiar with what measurements of dispersion are, measurements of centrality like mean, median, and mode. You should be familiar with different probability distributions and how we assess probability distributions. So we're going to start here in hypothesis testing. What is statistical inference? Hypothesis testing is one of the most useful techniques that people use to draw conclusions about the values of a population parameter using sample data or the differences among them. So, for example, when you have two parameters you're comparing, we can develop some hypothesis where these parameters are in numerical characteristics of the population and distinct from the sample statistic. So to do this, we formulate a hypothesis test. You basically have two contrasting hypotheses about a parameter you're interested in. You always start with the null hypothesis, which describes existing theory or belief, which is always assumed to be true in the absence of contrary data. Like the not guilty assumption until proven otherwise in the U.S. judicial system. So we have the null hypothesis is innocent until proven guilty, and the alternative hypothesis would be guilty. So our court system is trying to prove, or the district attorney is trying to prove the defendant as guilty. So you have the alternative hypothesis, which is the contrary to the null hypothesis. If this seems a little backwards because what you're actually trying to prove is actually the alternative rather than the one assumed to be true, I understand that, but it's just the way that we do things in the statistical world. So hypothesis testing procedures. So we are conducting a hypothesis, and this involves a few different steps. You formulate your hypothesis, both the null and alternative. If you're trying to prove, say, that profitability was statistically higher 1 year over a different year, the null hypothesis would be that profitability both years was equal, and the alternative would be that the profitability of the 2 years are not equal. And we have to select our significance level, so that is the confidence level that we are willing to accept. So, as it's going to be more and more difficult to reject the null hypothesis in favor of the alternative hypothesis, the higher we go in our confidence interval. So if we want to be 99% confident that we are not rejecting a true null hypothesis, it's going to require much more certainty in the data, much more validity of our data to give us that confidence. So we'll talk about confidence levels or significant values. So we use significant value as alpha, and alpha is 1 minus our confidence interval. So if we want to be 95% confident of something, we use an alpha of 0.05. If we want to be 99% confident of something, we use an alpha of 0.01. So hopefully you can see how that works. So step 3 would be determine a decision rule on which to base your conclusion. And then 4, we have to collect the data that's based off of our decision rule and calculate our test statistic. And then 5, we need to interpret the results based on our decision rule. So hypothesis, the formulation. So again, in formulating our hypothesis, the null is based on existing data or theory, or simply assumed to be true in the absence of contrary data. Then we have the alternative, and this is what we're trying to prove. This is what we're interested in seeking to see if it is actually valid. So what kind of test statistic are we going to use? What kind of test can we do? So this is based on what kind of data that we have and what kind of hypothesis we're formulated. So if you're just looking at one parameter, for example, you think the mean age in the class is 25, that would be a one sample test. If you have two parameters, you're looking at, say, for example, if you were comparing the mean age of this class to the mean age of a different class, that would be considered a two-sampled test because you would need two samples of data, so this class and another class, to formulate your hypothesis argument. So again, whether you're trying to prove the statistically requires proof, some evidence within the data. So to seek this evidence that supports our alternative hypothesis, say on average less than, so here we go, formulating the correct set of hypotheses depending on burden of proof. So what you wish to actually prove statistically is your alternative hypothesis, sometimes labeled H1. So we're trying to seek evidence that technical support calls average less than 25 minutes. So the correct hypothesis that we would formulate would be the null hypothesis, which is mean response times are greater than or equal to 25 minutes, and our alternative would be what we're actually trying to prove, mean response times are less than 25 minutes. It's very important when you're formulating your hypothesis test that you are mutually exclusive within your two groupings and you cover all possibilities. So when I say mutually exclusive, you see how we are greater than or equal to 25, or in our null hypothesis, and we're less than 25 in our alternative hypothesis. We can't have our null hypothesis say greater than or equal to 25 and our alternative hypothesis say less than or equal to 25, because now we're not mutually exclusive. We're both, the null and the alternative would be covering the value of 25. So if by chance we land on 25 minutes even, we wouldn't know where to put it. It wouldn't be, we couldn't reject the null hypothesis in favor of the alternative hypothesis, or we couldn't say that there's not enough statistical evidence in favor of the alternative hypothesis. So again, I'm just using the statistical language just so you guys get familiar with how we, how we proceed with our findings. So we got to be very careful on what language we use, because nothing's absolute in statistics, and so we just have evidence to say one way or the other, and we never accept anything as true. So just remember that, and I'll get into more detail about language here as we go through this lecture. So there's four possible outcomes. The null hypothesis is actually true, and the test correctly fails to reject the null hypothesis. So if the null hypothesis is actually true, we don't say we accept the null hypothesis, we say we fail to reject it, right? Because that's what we're trying to do, is we're trying to reject the null hypothesis in favor of the alternative. So that is the main goal through hypothesis testing. So if we come across a true null hypothesis, then our test correctly fails to reject that null. The null hypothesis is actually false, and the hypothesis test correctly rejects this conclusion. So if we have a null hypothesis that is false, what we would say is there's enough information, or there's enough evidence to reject the null hypothesis in favor of the alternative. You would never say we accept the alternative. If you go ahead and put that in your homework and I read over it, I'll know that you did not listen to this video, because I have reiterated many times that we don't accept anything. We just say we reject the null hypothesis or we fail to reject the null hypothesis. Those are our only two real options. And then there's other outcomes within those two options. So the other two options, or the last two options, are we have a null hypothesis that is actually true, but the hypothesis test incorrectly rejects the null hypothesis. So again, we're just using a sample of data, so we don't necessarily know if the null hypothesis is true or false based on the data that we have. We just have enough data to either give statistical evidence to reject the null hypothesis, or we have enough data available to us to fail to reject the null hypothesis. So if you collected the whole, say we incorrectly rejected a true null hypothesis, and in our sample we collected, say, only 100 observations, and the population was 300, and somebody else did a survey of the whole population, and they found contrary data to what we have, then the data points that we've collected were just not as representative of the population as we would have liked them to be. So again, look for chapter 3 and 4 about representativeness of data and survey techniques. So if we incorrectly reject a true null hypothesis, we call this a type 1 error. And going back to the judicial system, so our null hypothesis is saying that you're innocent until proven guilty, and this is a type 1 error is what we consider to be a really bad thing. It would be putting an innocent man in prison. That would be a really bad thing. And a type 2 error is pretty bad as well, but I don't think the court system looks at this as bad as a type 1 error. That would be letting a guilty man walk free. So using this, if we incorrectly fail to reject the null hypothesis, so if we believe the alternative is correct, but we don't have enough information to reject the null in favor of the alternative, and we find out later through collecting more data, or the whole entire population, that it's actually we incorrectly failed to reject the null hypothesis, we've done a type 2 error. And that, again, if you're innocent until proven guilty, the null hypothesis is innocent until proven guilty. This is saying that we are letting a guilty man walk free, that we weren't able to actually prove to the court system that that man was truly guilty, and so they walked free. So that's a type 2 error. Hopefully I didn't confuse you. Sometimes this example works with people, and sometimes it goes over their head and they don't, and it's more confusing. But again, if you want to use the judicial system in America, you're innocent until proven guilty. That's our null hypothesis. Guilty is our alternative hypothesis. If you put an innocent man in prison, then you've created a type 1 error, type 1 being really bad. If you have let a guilty man walk free, that would be a type 2 error, and that's also fairly bad. So we need to quantify our outcomes. And so to do this, we need to find our level of statistical significance. So the probability of a type 1 error occurring is actually our alpha. So if we want to be 95% confident, that other 5% is the level of error that we are allowed into our hypothesis test. And so that we call that alpha. And so if we want to be 99% confident of making, not making a type 1 error, so we want to really make sure that we don't put an innocent man in jail, then we go to an alpha of 0.01. So in testing, we usually choose our alpha, or no, we don't usually. We always choose our alpha level prior to formulating our test, and oftentimes prior to collecting our data in the first place. So there are some there's some norms, or different fields use different norms, but probably the most common alpha that's used is an alpha of 0.05. Sometimes people, if the probability of making it, or if a type 1 error is not as is bad, so I did soybean variety testing, and we were trying to differentiate between the varieties, and so we would go to an alpha of 0.1 because it wasn't necessarily bad to differentiate between them. To some extent it was, but it wasn't as bad as not being able to provide the farmers some distinction between varieties. So you might want to open up your alpha, make it a larger number if the what kind of consequences you would have for making a type 1 error are not as severe. And then there's the probability of correctly failing to reject the null hypothesis, which is our confidence interval. That's 1 minus alpha. So we go 1 minus alpha to get our confidence coefficient, or we go 1 minus our confidence level to get our alpha, or level of significance. And then there's the probability of making a type 2 error, and this is not normally calculated, but it is termed beta. So this is failing to reject the null hypothesis when it is actually false, and that's beta, and that's the power of the test. And again, that's something that we don't normally calculate. Sometimes if you get into more advanced statistics and you have certain models that do hypothesis testing a little bit differently, then you would calculate your beta. So the probability of correctly rejecting the null hypothesis when it is false is 1 minus your beta, and that's the power of the test again. So this table below, table 5.2 in the book, is extremely important. I highly recommend everyone getting very familiar with this and looking through, reading around that table to make sure that you have the understanding of the concept. So it is a table that we've probably seen before of a cross tabulation of the alternatives, the testing hypothesis, and the actual conclusion of those. So if our alternative hypothesis H1 is true, and the test rejects H naught, or our null hypothesis, then we're correct. If our alternative hypothesis H1 is true, and the test fails to reject our null hypothesis, we've just made a type 1 or type 2 error, excuse me. And if the null hypothesis is true, and the test rejects the null hypothesis, we've just made the type 1 error that we tried so hard to prevent. And if, again, the null hypothesis is true and our test fails to reject the null hypothesis, we're correct in that conclusion. So the decision rules. So we need to decide whether to reject or accept the null hypothesis, and this is based on computing a test statistic from sample data that is a function of the population parameter of interest, and compares and we compare it to the critical value, or alpha, from the hypothesis sample distribution and the test statistic. So in doing this, the sample distribution of the test statistic depends on which test statistic you employ, and is typically a normal distribution, a T or F distribution, or some other well-known distribution as outlined in chapter 4. So these distributions are divided into a rejection region, which is defined by critical values, and a non-rejection region. And if your test statistic falls outside the non-rejection region into the rejection region, you're able to reject the null hypothesis. So we're going to go ahead and visualize this in the slide here. So we have a normal distribution, as you see, and then on a two-tailed test, we have two rejection regions. So we divide our alpha, our level of significance, in half. So if we have an alpha of 0.05, we have an alpha of 0.025 on one side of the distribution and an alpha of 0.025 on the right side of the distribution. So we can do the same thing if we have a one-tailed test, and that puts all of our alpha on one side of the distribution or the other side of the distribution. So if our null hypothesis is mean response time is greater than or equal to 25 minutes, then our rejection region is going to be on the left tail of the distribution as seen here. If our null hypothesis is mean response time is less than or equal to 25 minutes, then we are going to have our rejection region or our null hypothesis area here, or I mean our alternative hypothesis area, mean response time greater than 25 minutes to the right side of our normal distribution, our bell curve. So when we say normal distribution, that means that we have a bell curve, and usually the mean, median, and mode fall at the exact same place. You have the same number of observations on the left side of the mean, median, mode as you do on the right side of the mean, median, mode. Again, this is not always the case. Most data is not perfectly distributed, but we have some relatively normal distribution that we have to meet. And again, go to previous chapters to review if you're unfamiliar with the terminology I just used. So one sampled hypothesis test. Test for means, variance, and proportions involving a single sample. So we can do this through a z-test if the population standard deviation is known, or a t-test if it's not. We almost always do not know the standard deviation of the population, so we most always use the t-test. We can use a z-test for proportions and a chi-squared test for analysis of variance between in one variable. So to do this, we have to collect a test statistic. So one sample test for mean, when the standard deviation is unknown, we use the t-value, and that is the mean of the sample that we collected minus the hypothesized value divided by the standard deviation over the square root of the number of observations you have in your sample. So for example, you have the customer support survey in the data set. So if you want to pull that up, we have tested the hypothesis. So we've outlined it where our null hypothesis is mean response time is greater than or equal to 25 minutes, and our alternative hypothesis is mean response time is less than or equal to 25 minutes. So to calculate this, we've calculated our mean of our sample, which is 21.91, our sample standard deviation, which is 19.49, and the number of observations in our sample, which is 44. So we just fill in within our formula. So we have the 21.91 minus 25 divided by our standard deviation over our square root of the number of observations. And we have a t-value of negative 1.05. So this falls in the non-rejection region. So we do not reject the null hypothesis because the t-value is of negative 1.05 is not less than the t-value of negative 1.68, which is our critical value for a one-tailed test with an alpha of 0.05, based on a degree of freedom of 43. So we have degrees of freedom for a t-test is the number of observations you have minus 1. And you can find the t-value and how the actual t-critical value in the back of the book. So if you go to your back of the book, there's a few tables there, and you can go ahead and go down for a t-test table. So critical values of T, table A2 in your appendix. For me, it's on page 512. You can look up the alpha and the degrees of freedom you have and find your critical value for each test. So again, to illustrate this, we have negative 1.05, which is still in the non-rejection region. So our gray area is the rejection region here. And you can see that negative 1.05 is greater than negative 1.68. So we fail to reject the null hypothesis. So using p-values. P-values is the probability of obtaining a test statistical value equal to or more extreme than that obtained from the sample data when the H naught is true. So if you remember, p-values are the probability of. So p-values can be chosen by the researcher, but generally we set p at alpha, at our alpha level of 0.05. So if you obtain a p-value less than 0.05, we can generally conclude that we have statistically significant results, and we can reject the null hypothesis in favor of the alternative. So when our t-value, when the absolute t-value is greater than the absolute critical value, we can reject the null hypothesis in favor of the alternative. And if our alpha value is less than, or if our p-value is less than our alpha, then we can reject the null hypothesis in favor of the alternative. So the p-value is directly derived from our critical, or our test statistic, and alpha and our critical value are related to each other, but they're inverse of each other. So as our p-value decreases in size, our test statistic is going to increase in size. So just to let you know. So it might help to just glance at table A2 in the appendix in the back of your book to kind of get some idea of how t-values and p-values relate to each other and how alpha and the critical values relate to each other. So long story short, when you run a test statistic, your results are typically always going to show a p-value, which is calculated based on your test statistic and the and are the comparison of its critical value. So our test statistic to our critical value is the same thing as comparing our p-value to the alpha. And if your p-value is less than or equal to your alpha, then you are typically safe to reject the null hypothesis. Your results are statistically significant, and you have found evidence to reject the null in favor of the alternative, to support your alternative. Again, don't ever say accept the alternative, please. Okay. So moving on to a two-sampled t-test. We do a two-sampled t-test when we are comparing two populations to test for differences in means, proportions, or variances. So again, mean of a two-sampled hypothesis test would be using a two-sampled t-test. Proportions would be a z-test for differences in two populations, or proportions, and a variance would be your f-test for equal variance. So we also have to adopt our t-test if we assume that the two samples have unequal variance.